today I'll be going over prototyping, a bunch of different tips and tricks, how to be efficient with your time while prototyping, and a bunch of different machining tricks to increase productivity. The goal is I'll be showing you guys some old school methods that we picked up pre-machines, or pre-big machines. And then after that, if we have time, we'll go into a little bit of milling and stuff like that. So, what is prototyping? Prototyping is creating a proof of concept in order to verify what you think will work. So, every year before we start with a question. What do we want our robot to do? Based on this, so for example, this year we determined the most important thing would be grouting cans. So based on this, then we go into phase 2, which is where prototyping starts, the how. So basically everyone will submit ideas that they have, and then based on what we think is most valid, those ideas will be split among different groups, and then those groups will be in charge of their ideas and their iteration. So there's a bunch of different materials. Basically, we prefer to use wood while prototyping. 254 prefers wood. It's light, it's strong, it's cheap, and it's perfectly good for proof of concepts. 254 actually creates an entire robot based on wood, or completely out of wood, that is almost identical to their final robot, simply as proof of concept. We don't go quite as in depth as them, but we do prototype a lot. So basically, our prototyping philosophy is that so we create our models, our scale models, and then once we see that those work, we try lots and lots of different variations in order to figure out if anything works better, what doesn't work, to break the system and figure out fixes, stuff along that line. Basically, on 1678, we want to fail as fast as we can to figure out how not to fail on the final robot. But even when you believe you are done with prototyping, you can still prototype. Our main example of that is 2013, or even this year. So your robot is not ever complete, especially with first 30-pound allowance. So we are constantly prototyping. In 2013, our robot was 3 different robots, depending on the event we went to. The only constant was the drivetrain. So we have a couple other things. So a couple other key mottos: steal from the best, invent the rest. So if you look at a bunch of our robots, lots of our prototyping had been done by other teams previous years. So our 2013 robot, or our 2014 robot, the flexi intakes, those had been done by Bomb Squad in 2008 Overdrive. If you look at our ground intake for 2013, the Poofs had a very similar system that we stole from, and then we invented more to add on to. So basically, you're creating a proof of concept as fast as possible. There are a ton of different machines, or a ton of different tricks for each machine. Basically, yeah, kind of have a lot going on right now, but so we go to what, the how. So one of the other main materials that we enjoy using is extrusion. Let's see. So how many of you guys have worked with extrusion before? It's very common. So basically, they're just different profiles of extruded aluminum, which allow you to be very flexible. The main reason is we have some on our new router that we haven't been running. But the extrusion, it allows you to slide on an axis very easily. So there's a bunch of different tricks. If you don't know the final position that you want, then all you have to do is add 2 T-nuts that slide on the axis that you think is most important to slide on. And then if you bolt a plate onto those T-nuts and bolt whatever you want onto there, you can slide before you figure out your final position. On our team, before CAD even starts, the final dimensions, we actually we do geometric sketches first. So these sketches are kind of leading to prototyping also. They feed both both projects feed off of each other. So rough dimensions can be obtained in CAD, such as in 2014, the height of and position of the intake rollers. We approximated those using CAD, and then we went through prototyping to figure out the fine details, the plus or minus less than half an inch required to actually suck up the wall. Another important thing of prototyping is documentation. So if you prototype but you don't document what you did, then there's no way to benefit from it. So our final dimensioning is determined based off of prototyping. We have this is just a little summary of our prototyping for 2015. As you guys can see, we actually built a square structure using our using an extrusion. So we actually built a square base using extrusion. Extrusion is just super easy to work with because you don't actually have to position things completely permanently. You just friction lock stuff with bolts and nuts. And then, so we figured out we created a base based off the allowed dimensions for this year, or last year. And then after that, we actually created a bunch of vertical slides, and we used these dimensions to prototype how we would actually obtain lift the toes and stabilize them. And as you can see, we started out with metal plates, but then those were too rigid. And this all happened within about the first week of build season. So we actually went through, we figured out the dimensions that would fit. We created the tabs. So we had to change material because there's not enough bend in these metal tabs. And then we started creating these plexi tabs. And then we went through various designs, including shark teeth, which we call them, basically little triangles to get the tabs on the toes to settle. But eventually we settled on just contacting in between those. And then, as you can see, after that we did a formal write-up, and we wrote all the dimensions, we drew them out, and we handed those off to the CAD team to input into the computer, which we then used to machine stuff. So, prototyping. A lot of the time we do stuff quick and dirty. Let me grab that here. So, a lot of the stuff I put in the box is stuff that we used before we had resources we do today. So if you guys look at these, it's a standard drill bit, or a spade bit, which is standard, which is generally used for wood. But because we didn't have a mill, a boring head, a lathe, or anything like that, we actually came up with a solution to grind these spade bits into a deep V so that only the outside corners are compacting. And this allowed clearance to go through aluminum, no problem. I'll actually be demoing that later if you guys are interested. Yeah, so lots of little tricks like this can help you prototype fast. There's a ton of other tricks you can do. So Devin, someone else was working on this presentation, created the term poor man's machining. Basically, it's working smarter when you don't have the resources. Lots of things you can do with that are full pattern jigs. So 5458 knows about this. So because they were a rookie team last year, and they didn't have all the resources that could have helped them, we actually created a couple of plays for them with different full patterns, spaced half an inch apart, and spaced half an inch into one inch section. So they would just place it onto their extrusion, and then they were able to drill. And then they just clamp and drill so that they're able to drill their holes all around the robot. This is also very useful for prototyping because milling takes a lot of time finding zeros and stuff. Well, instead you just clamp and go. Full pattern jig. So while doing prototypes, it's fairly difficult to do different angles, but you can always do right angles. And so if you create, basically, there's different ways of constraining things. When you want a certain angle, it's easier to, this. I'm not quite sure on how I want to word this. Okay, so it's easier to create a variable system instead of having to create a lossless system. So if you wanted a fixed angle, if you were to sandwich two plates and tighten the bolt down, then by constraining the two sides, you actually have the middle plate able to rotate. We did something similar to this while prototyping in 2014, which allowed us to figure out our final dimensions and angles for our intake. A couple other things to keep in mind are use of different extrusion profiles. So when you're using an angle, it's not quite as rigid as using a C or a full completed extruded base. So there's a couple of ways to strengthen those bases. One of them is by using standoffs and spacers. There are benefits and downsides to both. So generally, we tend to use spacers simply because you have a through bolt going all the way through. Do you guys know the difference between spacers and standoffs? Or go ahead. So we tend to use spacers simply because you have a bolt going all the way through, which when you tighten the bolt and nut, you actually create a preload on the system, which gives you stability. Another critical thing when you're doing prototyping is that you keep tolerances in mind. So lots of prototypes won't require you to be plus or minus 5 thou. Really, you can do most stuff by hand and just tweak until you find what works. And then once you go to test, or once you do the final machining, you go through those tolerances. While creating your active mechanisms, there's a couple of different things that are important. So we tend to like to use live axles, which are made very easy with the versatile planetary gearboxes. Whenever we're prototyping something, we just slap together a couple of those. Bean block wheels are actually critical, or we found them critical, simply because you could slide them onto the output shafts of the versatile planetaries, and they were a press fit, meaning that you wouldn't have to do any other fixturing onto them. And then after that, we mount the versatile planetaries on whatever we're working on. So in 2013, actually pretty much every year is applicable. So 2012, basketball shooter, 13 frisbee shooter, intake 2014. So back to this guy. When you have your axles either live or dead, sometimes it's the easiest way to grow a live axle is simply to have your flange bearings drop in place. So this is back to the 118 drill bit, simply a spade bit that we ground down. This will actually give you a nice slip bit, which is perfect for these bearings. When using the shafts, there's a couple other things to keep into consideration. Power transfer is important. So this has been made super easy with all the hex products that have been put out into the market over the past couple of years. Previously, people would have to mill slots or keyways into whatever they were working on, and then after that, they would have to get the keyway and put it in, or they could use shaft collars to that's other axis. Yeah, but basically, with all the different products that have been put onto the market, prototyping has gotten extremely fast. We love the Vex products simply because they're so versatile. You can use them in different ways. So literally every prototype we used last year, whether it was a tote chute intake or our elevator system, pretty much ran off of different hex shafts. Let's see. So proper constraining is key, especially on the shafts that you're using. There's a couple of tricks we can do. We have these shaft collars, which are the clamping type, which are extremely useful. But if you have an old school type and you don't have a hex shaft or a shaft with a spline or anything like that, then there's these shaft collars, which most people don't like because they have set screws, but a lot of people don't actually divot their shaft with simply a center punch or a drill, which will actually fix your shaft much more effectively. So when you have this set screw, it's a teensy set screw, you have it just running onto a round, it's able to slip easily. But if you were to simply take the set screw out and center punch through the hole, you create a divot which the set screw will lock itself into. Alright, so one of the easiest ways to make plates is simply to print it out once you've CAD'd it. This is an old trick that we use a lot, especially before we had the DROs. We would simply go into CAD, print the plate that we're using, and then on a drill press, you just drill any holes or features that are needed, and then you have a completed plate in sub an hour, depending on the complexity. So as we can go into machines. Yeah, so you guys have anywhere you guys want to start? Or any questions so far?
What kind of plates do you mean by like gearbox plates?
Oh, yeah. We've actually done gearbox plates by doing this. So we CAD the plates, we make sure that our printer is printing to scale, and then what you do is you glue the piece of paper onto whatever stock you're using, and you just drill out the crosshairs, and you can get pretty accurate. Yeah, there's a ton of tricks like that we use during prototyping. So, yeah, go for it.
How long do you guys spend prototyping? That's kind of something we've always struggled with, where it's like you split the time up and then all doing different things, but you don't want to spend a week prototyping. So how do you guys decide? Okay, that's enough. We're going to this. Do you have like a?
All right. So ideally, we're given a deadline. Usually, we're supposed to be done prototyping by week 3, which never happens. We always prototype more and more. This year especially, since we wanted fast can grabbers, we actually spent up until week 6 prototyping a 4-can grabber, which we were happy with until 3310 revealed there are 2-can grabbers, which were significantly faster, which restarted the prototyping process. So I would say that we want to be done with that midway through week 2 or week 3, but other stuff comes up which affects it. So as I said earlier, you're never really done prototyping. Even your robot is an advanced prototype. Go for it.
So after game reveal, January 1st, how do you guys start the thought process of, okay, our robot needs to do this, and how are we going to get it through this? Like you guys, I kick off. You guys just break up into groups? Do you guys kind of work together to do something?
So basically, once the game is revealed, we have everyone read the rules, and then we test everyone on the rules. Mike's analogy for this is you don't want to be the people playing soccer with their hands. So after we do that, then we do a point analysis of what we think is the best strategy for the game. And then based on that, that's when we finally decide the how. of what we're going to do. Usually we'll have students work individually. The students who have passed the test by this point, and this is day 2, so pretty much everyone. Then we'll have them actually draw up with their ideas for the robot. So after that, we will create tally marks based on similar systems, and then the students will vote on what they think is the most effective. And from there, that's where the prototyping groups actually come from.
Okay, so you guys kind of like rules for today, second day, ideas, and go.
Yeah.
We break down the rules, like all
It's
the
rules, strategy, and then the how we want to perform, how we want to complete what our strategy is.
So for these 2 ideas, so when you come up with a whole bunch of ideas, like you guys meet together one day and then just as a team vote on the ideas, the different ideas of doing something?
Yeah, so we meet the first 2 days after kickoff. So we meet the Saturday of kickoff and then the Sunday. And then usually we're still on break, which I'm not sure is true this year. But then we'll meet that entire week until school starts. And then repeat your question.
So what I was basically asking is you guys just come together as a team and then just take all the different ideas from everybody, put them together, and then just as a team vote on each idea, like to see how many
Yeah.
you can do.
Yeah, so we have our entire team at kickoff, and then we have our entire team read the rules. And then after that, each student is isolated so that there's no cross-contamination of ideas. I know this is really hard to pull off, but we tell our students not to share ideas until it's time to. Otherwise, someone else's idea might be forgotten, and that could be a...
So like, would you recommend having like everybody like get a sheet of paper and then write their ideas on how they build the robot and then like 12 pieces of paper and like one bin?
Yeah.
And then review each idea and like write it down on a big
Well,
chart and everything.
Yeah, so we actually do that, but we have our students present each idea to make it more clear of exactly what their idea is. We have our students, they're able to either draw a complete robot, or they can just go over a certain mechanism, anything that's really floating around in their head. And from there, we create tally marks that
Similar ideas.
of similar ideas, and we see what we think will be plausible and what isn't.
Can I just add to what you're saying? Because there's 2 things you're talking about here, which is the what and the how. So the what is what strategy are you going to implement in this year's game, right? And the how, right? You could be coming up with multiple ideas and you could prototype multiple ideas. But if you've determined the what, at least you have exactly what you're going to do. So that's almost more important. I think deciding on what strategy you're going to employ, which this year was like we were going to make stacks of 5. We came to that decision. We said we don't need to make stacks of 6. But we also came to the decision that getting the cans off the set was absolutely the most important strategy. And we pushed that strategy right to the end, as you all know, right? So deciding on the what first is very, very important, right?
How much experience do you guys have with machining? Sure, a lot of you guys have years.
The question's all.
One of the, even without CAD, we do a lot of stuff for prototyping simply by hand. Even for the final robot by hand. A lot of the times we'll just start with a piece of plate, and then we'll actually lay out what we're doing, and then go to a drill press and do it. So we have some plates that we'll just put somewhere over there on the table. So one of the easiest flashback techniques is instead of counting handles on a mill or something like that, all you do is we have something called plow fluid. We don't have any squeeze sharpies. What you do is you draw, you just coat your piece in a piece of ink, or coat your plate or whatever you're working on in ink, and then you input your dimensions onto calipers, and you use them to simply scribe across your plate. And by doing that, you're laying out your coordinates accurate to within a few thousandths which allows you to do that by hand. Yeah, so there's a ton of other tricks like that that we use. I have some more written down. You guys want to see that 8-inch spade bit in action? Or?
Sure.
Yeah. Cool. So over here I have a ton of safety glasses. If you guys ever have any more questions at any time,
You're just doing your job. It's very nice. You have to walk away.
Did you guys come to the go first?
Is this gonna? That's it? That's it? This side. This side.
Up until
Okay. I'm
last
just gonna hold this
fall,
up.
all we had was a tabletop jet mill, which wouldn't hold a tolerance of anything. Probably maybe like a 10th inch. Yeah, the thing was not rigid at all. It was just kind of completely. So, those are the table for the product that we're creating. So, doing this only go through aluminum, but simply because with steel, you'll actually go in. And the whole top fell off. Don't pass me that cute bottle. So. basically by modifying a spade bit, you're able to get a nice slip bit or a one-way branch bearing. This is probably one of the most used tricks by our team, especially before we got reamers. You guys want to check that out?
That was one way.
Yeah. So it's standard bearings, but it's nothing was common.
What was the modification that you did on the bit?
So if you look at the bit, I have a normal one there. But basically a normal spade bit has these points and then it's flat in here. So it'll actually cut through the wood by chipping at it. But on this one we just ground it so that it's a V and it only contacts the outside. So you're actually having it works almost the same as a boring bar. You're just contacting a small patch on the outside while you're drilling into it. Cool, so that's that. Another crucial trick we have is if you need multiples of a part, then we have, then simply by match drilling, you can create a second part. We use this all the time. The only thing to watch out for is make sure that your original part is your template for all the secondary parts. Otherwise, your tolerances start drifting all over the place, and you create non-functional parts. There's that. We have some other stuff. Over here. The way we do that is we get an timer by moving across on the by keeping one of your axes constant while moving the other. You know that you'll move across a symmetric part or a symmetric hole, meaning that if you take that distance that you move and divide it by 2, you'll end up at the center. And then if you do that for the other axis, you'll find this complete center for the hole. That's useful for finding your holes quickly. What else do we have? What about drilling this is one of the most fascinating tricks I found. If you were to drill a hole into something round, and you wanted to make sure that your hole was perpendicular to the piece, how would you guys do that? Anyone have a trick for that? Cool. So, after working on machines for a while, you pick up a bunch of tricks. But basically, this guy this guy. Same concept on the drill press as the drill press. This is a definitely for pressure for this guy. But the general idea is that by having something tangent to this, you're able to see where you are. So what I'm going to do is I'm going to put a center drill into the chuck and then lightly touch the surface of this. And as I move across, while the flow is unlocked, you can actually see the position of the tangent to the circle. So as you move across, you'll see this move until both sides are level, which means that you're completely centered on your part, which you can use as a throw to the center, and then you can move either side to side, or you can drill at that position. So there's lots of cool tricks like that that you can pick up. This guy has air. pressure on it to get the tank across. And then we have our perfectly perpendicular hole, or within a fraction of a degree. So these are some training parts that we were doing over the summer or over the past couple weeks. Basically, we were making shaft collars. We were actually preparing for prototyping in the fall because parts created in the off season aren't legal for the robot. We just created a bunch of different gearbox plates. For the versatilities, shaft collars, and we actually have a whole box over. You want to grab that for you or Megan?
I'm here.
Cool. So, do you guys have any questions about any machines right now?
Do you have any picture lathes?
These are one of the parts that the kids are making while they're being trained on the machines. This is another one. So these are plates for versatile gearboxes, and even though we have the mills, we actually make students do the holes on the drill press. Yeah, so basically we have the kids mark their piece, get calipers, spread out their position, their coordinates. Cool. So if you guys come over here, go back to this guy. Let's get down. So these guys are for versatilities. The reason they have slots is because odds are we're going to be driving something far away, so we're going to be using chain and sprocket simply to have the gearboxes out of the way. So that allows us to tension the chain. But all our other hole features, like this one, were sharpied onto here and then scribed, and then the students would simply center drill it. This is another trick for the drill press. Basically, the table. So, whenever you're drilling, you don't know perfectly where your drill is going to be. So, what my former boss taught me. Cool. So, try this guy on. So, a nice trick is you go down, and then because the center drill is pointed, I have to slide this over, otherwise hit the lights. Cool. So what you do is turn your drill on, you get a center drill, and you simply move down until you think you're close to the scribe line. And once you think you're close enough, you just give it a slight tap. And then I'm not going all the way through so I can show you guys. But once you give it that slight tap, it'll actually show you where you are on your crosshairs that you scribed out. And based on that, you can compensate. So if you guys look at the little divot that I made, pass that around. You can tell how centered it is by the position of the circle.
So then you get the bit and put it.
Yeah, then you'd go through deeper with your center drill. You just give it a light tap so that it just mars up the surface. And you reference that to your crosshairs. And then once you're satisfied with it, you go all the way through, or you create your taper with a center drill, which guides your drill in. Go for it. Any questions about that?
About that, but you just have you have cubes of grinders and you also have the belt sander.
Yeah.
What are there any situations like how do you differentiate the situation between the sander to a belt?
So we have a couple different grinding wheels. We primarily use the grinding wheels for tool steels for the lathe. So we buy a bunch of blanks, which are just really hard steel that have been heat treated. And then you actually grind the shape based on what cut you're going to make. This wheel right here is the deburring wheel, which we use just for burrs on aluminum or steel. And then the belt sander we tend to use for wood. All our belts are fairly aggressive, so they're not the best for metal. They also tend to wear faster than the wheel. While the wheel gets smaller, it's still good for a lot longer. We have, where our lathe is. Basically all of our bits, or all our tools for the lathe have been ground by hand. Yeah. So we're back to the mill. Basically, we had this trick, which enabled us to drill a hole perfectly perpendicular. Where that plate went, it's still being passed around. Yeah. Has everyone got a chance to see that? Okay. So I have the finished product over here, and we have a few that we've actually tested, but by hand we were able to get within the tolerance of the bolt pattern on VersaPlanetary. So these guys are extremely useful, and I suggest making these during the off-season. So another useful part for prototyping is if you want to power something with pneumatics to remove the human element. Whenever we try to move something manually, we tend to overcompensate even without thinking about it. So another practice part we're making are these clevises, which mount onto any Bimba cylinders that come in the kit of parts. Those are extremely useful for prototyping.
Like Anthony said, I don't think the process ever stops. We continue prototyping pretty much throughout the entire season. But it takes a lot of different forms. So at the beginning, we start with really basic prototypes. So like the ones you see in the pictures, just an extrusion frame with linear rollers, creating elevators so we can test fingers, how we actually lift the toe, how much of the toe can actually stick into the elevator, those kind of things. And after we get those dimensions, we're actually able to commit a lot to CAD because we do use a lot of CAD during our design process. So we're able to commit the elevator's structure. We know where the fingers have to be mounted within the elevator carriage. And then we can start developing things like how we're going to move the carriage up and down, how to package that within the robot. So that can be committed even though we're still continuing prototyping, like integrating intakes, etc. Yeah.
Okay, back to CAD. Even simple part drawings could be useful prototypes. So as soon as we figure out what the dimensions of the balls are, or whatever the object for the game is, we simply draw that on a sheet of paper to scale. Draw the size of robot you're allowed. So you just draw a simple base, front and side view, and then based on that, you can start drawing shapes and figure out what how the game object fits into your robot. So that's actually one of the most useful things that we start out with, even before getting to physical prototyping. It's just simply drawing and figuring out what dimensions are possible.
You did a good job. You answered all the questions ahead of time.